Good morning, everyone. Mrs. Basega here, and today we're working on work and power. This is the review for the Unit 4 test. All right, so once you open up Formative, a thing to keep in mind is that there are 40 questions. Go through this once, see how you do. I only put auto scoring problems on this. Then, after you check your answers, then watch this video and skip ahead to the problem that you need. So if you got numbers 24, 29, and 38 incorrect, skip to that part of this video. You don't need to watch this whole thing. All right, so let's start off. I've got my equation sheet and calculator beside me. I've got a piece of note paper to help me if I'm doing a more complicated calculation, and you should have those items too. For number one, if the sign of the work is negative, then the force is in the opposite direction to the displacement. The force and distance would be in opposite directions to each other, so that means it would have an obtuse angle. An obtuse angle means the work done is negative. So if the force is to the right, but the distance the object moving is to the left, this puts a 180-degree angle that is obtuse and work would be negative. For number two, the force as a function of displacement means that they have a force on the y-axis and displacement on the x-axis. This work is done by taking area under the curve. Since this is a triangle shape, I'm doing in my head that the work is equal to 1/2 base times height, or 1/2 a base of 8 and a height of 5, to get something along the lines of 20 joules. This work done is positive. Since this is just an object that's moving, I would assume that this is adding positive work. It's adding kinetic energy to the system. Similarly, calculate the work done on the wagon. This is going to be taking area under a curve again. But notice this time that I have two triangles plus a rectangle shape. So I'm going to treat all of these separately. So just to split it up, I've got a triangle to the left. Its area, its work that would be done on the wagon would be would be zero point 0.5 base times height, would be zero point 0.5 with a base of 4 and a height of 10. That's the first triangle on the left. This gets 20 joules. The rectangle in the middle would be base times height with no zero point 0.5 out front. It has a base of 2 and a height of 10, so it also does 20 joules of work. Finally, in the last section, that's a triangle. Its base is not 12. Its base is 6, and its height is 10. So that's 0.5, 6 times 10, or 30 joules. All in all, this adds up to a total of 20 plus 30, or 70 joules. So I'm going to type in here 70, and with the 70, you don't need to put positive or negative. You don't need to put units because as a calculation problem, it's actually just checking how close is this number to the one that I'm expecting. So for number four, I'm going to use a tool that you should be very familiar with at this point, energy bar graphs. At the bottom, we're assuming that Lucy is at the reference line. We're assuming that she is not above the ground. We're assuming that reference line is 0. So there's 0 gravitational, 0 kinetic, and 0 spring in her first picture. But by the last picture, she's gained gravitational potential energy. And since work added that energy to the system, she must have done positive work. And those values should be equal. That means the work is equal to 40 kilograms times 9.8 is g times a height of 0.25 meters. That gets me a work of 98 joules. So I'm entering here. Remember, this is a calculation problem. So 98, don't include joules, don't include units, all that good stuff. Similarly, for power, power is work divided by time. You could also think of power as energy divided by time because she's transforming this into gravitational potential energy. So we could do work divided by time now that we know the work is 98. Or we could do mgh divided by time. because we know that she has moved this object to gain gravitational potential energy. In either case, it'll be 98 divided by 2, or in this case, that is 49 watts. A similar problem is number 6. A 300 kilogram ski lift was raised 50 meters in elevation in 2 minutes. I know that this is adding gravitational potential energy. Assume that your ski lift starts at the bottom and increases its height, so it gains gravitational potential energy and therefore does positive work, adding energy to the system. Using the same situation as we just did with the Lucy problem, power is work divided out by the time. But the work is also equal to the gravitational potential energy she does every second. So the ski lift, when it moves a 300 kilogram ski lift through a 9.8 gravitational field to a height of 50 meters in 2 minutes, a special thing to keep in mind here is 2 minutes is 120 seconds. That yields a power of 1,225 watts. Now, if you're looking at this and you're like, oh, wow, there's not an answer that's super close here. That's because if you use 10 instead of 9.8, then you get 1,250. Round to the nearest number if you can't find one that's close to the one you calculated. All right, so 7, 8, 9, they're all going to use this particular picture. So make sure to refer back to it as you go. I can see off the bat that normal and gravity will not be doing any sort of work. So I'm going to grab those as 0 to start off. Normal and gravity don't do any sort of work because both of those are perpendicular to the direction of distance. So let's say I make my distance vector to the right. The normal force was going upward. So that means that its angle would be 90 degrees. And when I do cosine 90, that always gives me 0. And 0 times anything is always 0. So a thing to keep in mind is that forces that are perpendicular to distance, or displacement in this case, forces that are perpendicular to the displacement of your object do no work. So gravity and normal don't speed this object up and they don't slow it down because they're directed perpendicularly to the direction that the object moved. If my angle were acute instead, it would do positive work. Any angle from 0 to 89 degrees would do positive work because the x component of this vector, the amount of the applied force that's in the direction of motion, actually helps speed it up. So notice that the x component of the purple vector is in the same direction as motion. And so it's trying to speed up the object and add energy to the system. Forces that are acute then do positive work and add energy to the system. So the applied force is going to do positive work. Now I know that I have to use the equation. I know it's not going to cancel out and be 0. So the work done by the applied force is force times distance times cosine of angle. In this case, the force is 150 newtons. The distance is 4 meters, and it's cosine of 30 degrees. Make sure your calculator is in degrees here. This gets positive work of about 520 joules. It's 519.6. We will call this 520 joules. This adds kinetic energy to the system. Last one, let us do the work done by friction. The work done by the frictional force is negative, and it has to be negative because friction tries to take mechanical energy and turn it over to heat. So if the displacement of your system was to the right and friction is acting to the left, this is going to have negative work because of the obtuse angle. In this case, I see this angle is 180 degrees, and I'm going to use that when I do FD cosine theta. So the work done by friction is going to be 60 newtons, that's the friction force, times a distance of 4, times a cosine of 180 degrees. Not the 30, because the friction force and the displacement don't form a 30-degree angle with each other. They form a 180-degree angle with each other. This gets me negative 240 joules. This is going to be removing energy from the system and taking it into a different form that is non-mechanical, namely heat. Notice that with the choices provided in 9, that you actually didn't have to calculate anything. Knowing that friction does negative work means that the only possible correct answer was A. Now, it doesn't ask this, but just for funsies then, this means the net work done in the system would be the work done by the applied force plus the work done by friction force plus the work done by gravity plus the work done by normal would be 520 plus 0 plus 0 plus negative 240. This is going to get us a positive work. Overall, this is going to speed up the system. This is a positive work of 280 joules. This adds kinetic energy to the system so that our diagram would have positive work, adding kinetic energy to the system, while all the other energies remain zero. If you wanted to, after the case, you could notice that work is equal to the kinetic energy that was added to this block, and we could use that to find a missing speed. Because we know that the work done is 280 and the mass is 20 kilograms, we could figure out that, all right, the work added energy to the system. We could figure out the missing speed by dividing by 10 on both sides, taking a square root, and this gets me the final speed of the box is 5.3 meters per second. So even though that wasn't asked, I think that section was important for a reason. For number 11, recall that the applied force did positive work and the friction force did negative work. So these two did work. However, the ones that did not do work were at 90 degrees. The gravity and normal force were at 90 degrees, so they did not do work. Number 12 and 13 are trying to get you to connect kinetic energy to mass and speed. So when it says which of the following bodies has the largest kinetic energy, why don't we just make m equals 1 and v equals 1 and solve this out here? So in this case, this means kinetic energy for choice A would be 1/2 times 3 times 1 squared would be 1.5 joules. That's my choice A. Choice B, kinetic energy of 1/2 times 3 times 2 squared. This gets me 6 joules. And that makes sense because having more speed means more kinetic energy. What about choice C? A mass of 2 and a speed of 3. Oh wow, that's going to be big. That'll be 9 joules. And finally, a kinetic energy for 4 would be 1/2 times 1 times 4 squared. When working with a proportion problem, a tool you can use is to set the numbers equal to 1 and just solve them. This means that A has a mass of 3 and a speed of 1. And solving all of this out, I can evenly compare my answers, and I see that C has the largest kinetic energy. Similarly, let's do the same exact thing for 13. For 13, it's a mass m, a speed v, and it says the mass decreases while the speed doubles. So the original object has a mass m and a speed v. So let's put in 1/2, m is 1, v is 1 squared. So this gets an original kinetic energy of 0.5. The new kinetic energy then would be 1/2 times 1/2, and the speed is 2 squared. This increases the kinetic energy to 1 joule. So in this case, it doubles the kinetic energy from 0.5 to 1. And since it doubles the kinetic energy, then we can say that it is increasing. It has twice the original kinetic energy. Number 14, two objects are lifted above the ground, which has the greater gravitational potential energy. Let's just MGH this. PEG is equal to mgh. The one on the right has a mass of 2. Gravity, I'm going to call G 10 just to make my math easy so I can do it in my head. This means that the gravitational potential energy is 120 joules. The one on the left is PEG. Let's call this a mass of 4 times 10 for gravity and a height of 3. And this also equals 120 joules. So those will have equal gravitational potential energy. For number 15, the potential energy is greatest when the ball is highest above the ground. So if you can imagine that this is the path a projectile would take, except cleaner, then it would have the largest amount of potential energy just when it reaches the highest point in its flight, the apex of its motion. The ball will have the most gravitational potential energy at B, the highest point in its flight. For springs, be able to calculate the spring constant from a graph. This is what we were doing in that lab, right? So we're trying to find K. We know a force and displacement, and literally pick any value of here. I'm going to pick the last one. So this is a force of 6. Solve for K with a displacement of 0.1 meters. Make sure you change 10 centimeters to meters. Dividing by 0.1 on both sides gives K is equal to 60 newtons per meter. For 17, you have 2 choices. You can use your potential energy as 1/2 kx squared. So in that case, that would give you 1/2 times a K value of 60 times 0.1 squared. This gives a spring potential energy of 0.3 joules. But alternatively, maybe a faster and more reliable way would be to notice that the energy added to the system is also equal to the work done on the system. This would be taking the area under the curve of this triangle. The reason I say this is more reliable is what if you calculated the spring constant wrong? If you take the area under the curve, it doesn't rely on your previous answer. So if I did the energy is also equal to the work that was done on the system, I could take the area under the curve, or 0.5, times a base of 0.1 meters, times a height of 6 newtons. This would get me also 0.3 joules. Notice that they add up, they're equal to each other, and they should be. They should be equal to each other because the work done in stretching the spring, 0.3 joules, should be equal to the energy that was added to the spring, also 0.3 joules. So you could take either method in order to determine the work/energy being done in this spring. For number 18, I'm going to have you think about this for a second in terms of this graph. How does the elastic potential energy stored in a spring change if the compression is doubled? Again, I'm going to show you 2 methods how to solve this. If the compression is doubled, that means the displacement of the spring goes from 10 centimeters to 20 centimeters, about here. That would also mean that the force increases on the spring. So both the x-axis will double and the height of this triangle will double. This gives you more than double the energy stored. In fact, if you notice here, this actually quadruples the energy stored. If originally it stored this much energy with the highlighted purple triangle, if you double the distance, then you double the x-axis, so you're doubling the base, but you're also doubling the force because as the spring stretches farther, it increases the spring force. So you're doubling the base and you're doubling the height. So you do 4 times the work. It would do 4 times the energy. Alternatively, you can do the proportions method. You can say that if you are doubling the spring compression, then originally you had a spring that did 0.3 joules of work. Let's say you took the same spring with 1/2, a K of 60, and double the spring compression to 0.2 meters, and that'll be 0.2 squared because it's 1/2 kx squared. you would see this is 1.2 joules. In either case, either by picturing it as quadrupling the area or by substituting in real numbers, we see that the elastic potential energy will increase by 4. For number 19, we want to have half the spring constant. That means it's going to take less force to stretch the same distance. So let's grab the draw a straight line tool. And if you haven't noticed this before, where it has this line picture, sometimes it's on Scribble. If you click on it, it will allow you to draw a straight line. So I want something that would take half of the force to stretch the same distance. So I'm drawing a slope that is half. This takes less force, a force of 3 newtons, to stretch the same distance. For number 20, a roller coaster is shown in the diagram below. At A, it's at rest. That means at point A, there's all gravitational potential energy. At points B and E, the gravitational potential energy would be 0 because they're on the ground. So let's put A as the highest gravitational potential. D has the second highest height, so would have the second highest gravitational potential. C would be the second lowest, and B would be the lowest gravitational potential energy because it's on the reference line. As a reminder, the reference line means that anything on this line has gravitational potential energy of 0. So both B and E would have 0 gravitational potential energy, and A would have the highest because it has the largest height above the ground. Since mechanical energy is conserved in the system with no friction, air resistance, any other external forces, mechanical energy is conserved, and that means that the gravitational potential and kinetic energy are inversely related. Having more height means you have less speed because a smaller portion of your energy is going towards kinetic. So A would be the slowest this time because most of its energy is in its gravitational potential, so none of its energy is in kinetic, and it is not moving. So I'm actually just going to reverse rank these. So A was my highest gravitational potential energy before. A must be my lowest kinetic energy. B was my lowest gravitational potential energy. It must be the highest kinetic energy. Switching my C and D values gives the rest of our ranking. If friction were included, though, a larger percentage of the mechanical energy would get switched over to thermal as it travels. So if friction were included, the speed would be greater at point B because friction hasn't had the time to take as much energy out of the system. For 23, a toy roller coaster is launched at point A by a spring. At point B, it is halfway up and is still moving. So at A, it has elastic potential energy, and at B, it is above the ground and moving. For 25, a 0.2 kilogram block is placed on a spring with a spring constant of 150 newtons per meter, and it is also compressed a distance of 0.2 meters. At point A, it has spring energy. At point B, it is unmoving. Notice it reaches its maximum height. At its maximum height, it's unmoving. So when I go do my energy bar charts here, I expect to see, I'm going to choose the rectangle shape. I expect that there's spring energy to start. That turns into gravitational potential energy at the end. But it also says to include the energy equation in the system and flow. So I would call this the block earth spring system. And then my equation would be PES equals PEG because there was no work done on this system from external forces like friction. Number 26, calculate the initial energy of the system at point A. Well, now let's look back at our diagram here. My initial energy was all spring potential. So in this case, I can calculate the spring potential energy. That's 1/2 kx squared. That's 1/2 k is 150. X is 0.2, 0.2 squared. This gets us a spring potential energy of 3 joules. That means if the spring potential energy was 3 joules, then the gravitational potential energy at the end was also 3 joules. So let's bring that value down. Let's record the initial energy. The initial energy is 3 joules. That means the final gravitational potential is also 3 joules. So I can use that to get our maximum height here. In this case, that means PEG must also equal 3. So MGH equals 3. That's a mass of 0.2. It says use gravity as 10. A height is unknown. And let's solve for H. Dividing by 2 on both sides, H equals 3 over 2, or 1.5 meters. Since this is a calculate problem, you'll notice that I don't need to include units or anything. I'm just going to call this 1.5. Conservation of energy with work. A truck driver slams on their brakes. They're moving a constant speed v, traveling a distance d. So friction does negative 4,000 joules of work on the moving car. How does this affect the kinetic energy? Well, think of your energy bar graphs, my friends. It has kinetic energy to start. And how much energy does it have at the end? It's not moving at the end. It's not above a hill. It's not touching a spring. Well, that must mean that the work done was equal to the kinetic energy. So if I drew 6 bars before or 7 bars before, I should be drawing 7 bars again. The work is equal to the kinetic energy. In this case, the work is the negative. It decreases the kinetic energy. So if friction does negative 4,000 joules of work on the car, that must mean that the kinetic energy is decreasing by 4,000. Now, if the driver had been traveling twice as fast, that would mean they increase their kinetic energy by 4 times. And if you're having trouble picturing this, this is because if you have that v squared, so I'm going to put a proportional symbol, the kinetic energy is proportional to v squared. So if you do twice the initial speed, that actually gives you 4 times the kinetic energy. So let's write this in words. Twice the speed gives you 4 times the initial kinetic energy. So that means if you were trying to stop the car, it would take 4 times the distance in order to do so. For number 30, before the truck starts braking, that means there's kinetic energy. And after the truck has come to rest, the friction has done negative work, so there's thermal energy at the end. For number 32 and the ones that follow, a person's car has broken down and now they're trying to push the car. This is another work problem. The distance the car moves is to the right. The force that's being applied is also to the right. So in this case, the angle between the purple and red arrows is 0 degrees. So the work done by the applied force would be FD cosine theta. That would be 200 times 12 times cosine 0, or in this case, that would be something like 2,400 joules. This work done is positive. So if at the same time I'm imagining my bar charts here, it starts with 0 energy. It's not moving, it's not above the ground, it's not touching a spring. We do positive work that adds kinetic energy to the system. So if I know that the work is equal to the kinetic energy, I can set my 2,400 equal to KE and solve for speed. So kinetic energy is 1/2 mv squared. So that's 0.5 mv squared. Substituting in, that'll be 0.5 with a mass of 1,200. Solving for speed. So first thing I need to do is multiply. This will give 600 v squared. Then divide. So dividing 2,400 by 600 gives me 4. Then square rooting everything gives me 2. So the speed is 2 meters per second. Next, a 0.5 kilogram block sits on a spring with a spring constant of 48 newtons per meter. And at point A, it's compressed a distance of 0.5. The total initial mechanical energy at A would be all spring potential energy here. So let's figure out that amount. When I go calculate mechanical energy, that's kinetic plus gravity plus spring, that'll be 0 plus 0 plus 1 half k x squared. So that'll be 1 half a k value of 48, an x value of zero point 0.5 squared. This gets me an initial kinetic energy of 6 joules. Now at point B, there's some gravitational potential energy because it's above the ground. So using mgh for my gravitational potential energy, PEG is equal to mgh with a mass of zero point 0.5, let's call G10, and a height of zero point 0.6. This gets me a gravitational potential energy of 3 joules. Okay, my friends, a tricky thing is about to occur here. Normally, if there was no friction, I could then say that the kinetic energy in the final system is 3 joules. But notice that we know the speed here. How much kinetic energy is in that final picture? Pause the video and try this on your own. 1 half mv squared for this particular problem gives me a mass of zero point 0.5 and a speed of 2 squared. Kinetic energy is only 1. That is less than we expected. And if you're following along on our energy bar charts here, this means there is 1 joule of kinetic energy, 3 joules of gravitational potential energy, 6 joules of spring potential energy. But guys, 4 does not equal 6. There must have been negative work done here. The work done by friction, notice it says, do not ignore the friction. The work done by friction must be negative 2 joules, because this means then that 6 minus the 2 joules of work done by friction gives us 4. So friction must have done negative 2 joules of work in order to decrease the energy in the system. That means for number 36, you and I have already done the calculation. The final kinetic energy at point B was 1 half mv squared, or 1 joule. Similarly, for number 37, you and I have already completed the energy bar chart on the side, so this is just copying it over. Notice that I'm going to use the potential energy to start, converted to 1 joule of kinetic for the teacher, 3 joules of gravitational potential, and that means 2 must have been lost to friction, and friction turns energy to heat. All right, so the sign of work done by friction is negative because it's taking energy out of the system and turning it to something non-mechanical, namely thermal. And the magnitude of the work is 2 because think magnitude is absolute value. The energy removed from the system by the work done by the frictional force was turned into thermal energy, or heat, and then hit submit, and you're done. All right, best of luck on your Unit 4 test. Thanks, guys.